Hello everybody, welcome back. We're going to finish on chapter 10 today. I mentioned in an email to all of you, but you may not have read it yet, that as we discussed previously, the exam 3 has been postponed. It was supposed to go through today, so it's a good thing it was postponed, right? But in any case, the dates are June 6th through the 8th. I didn't push it further back than that because I realized if I did, you would have like maybe 1 or 2 days and then the final. So we're sort of splitting the difference here on a tough end to the semester. The exam will cover chapters 7, 8, 9, and 10. We finished 10 today. Practice exam 3 is posted. And be sure to read, before you look at the key, be sure to read the note I've got on the content page about some of my own continuity errors. There's some problems that I required in previous iteration of the class that I didn't require this time, but some of those answers are still on the key, so don't worry about that. Anyway, read the note. It should be pretty straightforward, and let me know if you have any questions. All right, we've been talking about addition to alkenes, and we introduced, I think, 4 new reactions last time, but it was basically 1, maybe 2. Go ahead.
How many chapters will we cover after the third test?
After the third test, starting today, we're going to do 11 and 12, and then there's a spectroscopy section, sections A, B, and C, and that'll be it. So, I mean, it's still kind of some. All right, we introduced 4 new reactions, which was basically 1 new reaction. We talked about hydrohalogenation, and this is where you add HCl to an alkene, as we talked about. The Cl ends up on the more substituted carbon. And if we used deuterium here so that we could tell the difference between deuterium and hydrogen, you get a mixture of syn and anti products. The regioselectivity here is for the chloride ending up on the more substituted carbon, which your text calls the Markovnikov rule. And in terms of stereochemistry, you get both syn plus anti, and you get, whenever you make chiral products that would be chiral, you have to make a 1-to-1 mixture of enantiomers. And the motivation for this is that, the reason for this, rather, is that you have a carbocation intermediate, right? The pi electrons attack the hydrogen. One of the 2 carbons, A and B, gets the hydrogen. The less substituted one gets the hydrogen, so that the more substituted one can have the positive charge. And then the nucleophile can attack from above or below. It's exactly the same for alkene hydration, wherein you see, we could see basically the same products, only it would be an alcohol instead. Mechanism here is exactly the same. We're regioselective for the OH on the more substituted carbon. In terms of stereochemistry, you get syn and anti-diastereomers, and then you get also 1-to-1 mixtures of enantiomers. All right. Questions about that? Yeah.
For hydration, it's optional with the acid use, correct?
I'm sorry. Say that again. I missed it.
For hydration, which acid you use?
Okay. Yeah. For hydration, which acid you use is optional. It's catalytic, so you don't need a lot. You wouldn't use HCl because then the nucleophile that comes in is going to be Cl minus. And you could argue over why water doesn't outcompete Cl minus, but presumably it does outcompete the conjugate base of sulfuric acid. But the answer I'd have to give you is I don't know. Yeah.
Cool. Okay, I was confused.
Yeah. Equally confused. Yep. Yeah, the issue is just both of these are aqueous acids, so why does chloro come in here, but water comes in there, and all I got is maybe HSO4 minus is a bad nucleophile, but that's just more of hand waving than a real reason. All right, we introduced another couple of reactions where we saw halogenation of alkenes, we saw exclusively anti-products, and this is because you never form a carbocationic intermediate. Instead, you go through a bromonium ion that looks like this. Both carbons get a bromine, so there isn't really a regioselectivity issue here. The stereoselectivity issue is that we only get anti. Of course, we would still get a one-to-one mixture of enantiomers. As we start out with a chiral product, or a non-chiral, as we start out with a non-chiral starting material, if we make a chiral product, we have to get both enantiomers. And then we made the issue just a little bit more complicated by saying, let's do bromine, but let's have an excess of some other solvent. We used water and or alcohols before for this. I'm just going to use water. What we saw in this reaction is that the OH group would still end up anti to the Br, but that the OH group would be exclusively on the more substituted carbon. And we rationalized this by saying that the transition state for this reaction is very similar to the transition state for epoxide opening. Br plus here in the bromonium ion is an excellent leaving group, so it leaves partially from the more substituted carbon, which can better tolerate a negative charge, the buildup of positive charge in the transition state. And that happens to a large extent while the nucleophile is still far away. And so the issue of regioselectivity is OH on more substituted carbon, but you could think of that as sort of a Markovnikov principle. The second thing that comes onto the most substituted carbon. And again, on stereoselectivity, you get anti only. And then, of course, if your starting materials are not chiral, you have to have a one-to-one mixture of enantiomers. So that's your whirlwind review of where we've been so far. The last alkene reaction we're going to do, the last addition to alkenes we're going to do in this chapter involves something called hydroboration followed by oxidation. So these aren't the same reaction. This is a 1-2 sequence of reactions. And so we need to introduce the hydroboration reagent, and this is BH3. And there are other things that work as well. In fact, there's sort of a number of other weird hydroboration, oxidation reagents. Somehow I don't like that, I don't know. Where we substitute carbons, hydrocarbons typically. You saw one on exam 3 where there was some weird sort of chair stuff going on out here. I won't make you memorize any of the other hydroboration reagents, but as you see them in the text, they're going to function exactly the same way as BH3. Okay, so the players are a little bit different here. However, the considerations are going to be the same. Our nucleophile is going to be the alkene, and we're going to be thinking about the highest occupied molecular orbital, which is the carbon-carbon pi bond. Again, we've been drawing this as sort of what we expect a pi bond to look like, shared between carbons A and B. And even if we don't know a lot about this reagent, I will tell you that boron, or the BH3, is our electrophile. And as you learned on exam 2, the LUMO of that electrophile is the empty p orbital on boron. Okay, so what we're going to do now, recognize that before, when the LUMO, or I'm sorry, when the HOMO of the alkene attacked the LUMO of the acid, that was a sigma star anti-bonding orbital, and so we had to break a bond. We're going to do basically the same thing here, only this is a non-bonding orbital, so we don't necessarily have to do anything right away. All right, so what happens is boron approaches the alkene. Pi electrons attack the boron, and we start to form, I'm going to start drawing the transition state here. As that happens, and I'm going to use a dotted line here to indicate that the pi bond is breaking, and a bond here to indicate that the bond between boron and carbon is forming. Okay, if we made a full bond to boron, it would be bonded to 4 things, so that would tend to build up negative charge on boron, right? So I'm going to tell you that in the transition state, that already starts to happen. We build up formal charge on boron, and whichever of the 2 carbons of our alkene we start to make the bond with, the other one's going to have a corresponding buildup in positive charge, right? So because of course the HOMO is shared between the 2 atoms A and B, but as we make a bond, the bond is only with one of those carbons, so we start to make the carbon-boron bond so that in the transition state a buildup of partial positive charge can be on the more substituted carbon where it's more stable. All right. Now, one thing that you may not know about boron is that it's not very electronegative. In fact, if you look up the number, it's actually less electronegative than hydrogen. Oh, that's weird. So what does that tell you about the polarity of these boron-hydrogen bonds? More electron density in the hydrogens. Good. So what I'm drawing here is the symbol for a dipole, and these dipoles are aligned along each of those boron-hydrogen bonds. And the reason this is the case is because hydrogen is more electronegative than boron. So in the transition state, actually that partial negative charge, which we said would be on boron in terms of formal charge, remember, formal charge is just about keeping track of electrons. It doesn't necessarily tell you where electron density is. It turns out that a lot of it is out on these hydrogens. Okay? So do you understand the argument there? We're taking a neutral reagent, we're making a bond to boron. If we made a full bond, had boron bonded to 4 things, the boron would have to have a negative formal charge. In this case, we've only partially formed the bond, so we put a partial negative charge on boron, but then we considered electronegativity, and we concluded that most of the partial negative charge would have been out on the hydrogens. Okay, do you follow that reasoning? Okay, so as the reaction begins to occur and negative charge starts to build up on the hydrogen here, that hydrogen, as being negatively charged, starts to be attracted to the growing partial positive charge on carbon. And that leads in the transition state to weakening of the boron-hydrogen bond and formation of the carbon-hydrogen bond. All right? Yes?
Is there a partial negative charge on each of the hydrogens?
Yes, there would have been a partial negative charge on each of the hydrogens. Perhaps maybe more on the one that's close to the partial positive charge, I guess. So you have a transition state here where a lot of things are going on. In the transition state, the carbon-carbon pi bond is breaking. The carbon-boron sigma bond is forming. The carbon-hydrogen sigma bond is forming, though the carbon-boron bond is forming to a greater extent than the carbon-hydrogen bond is forming. If we wanted our drawing to reflect that, I sort of tried, but if we wanted our drawing to reflect that, we would show the boron carbon dotted line to be smaller than the boron hydrogen dotted line. In any case, the idea is that if we form the carbon-boron bond quicker than we form the carbon-hydrogen bond, there's a significant buildup of partial positive charge on the more substituted carbon where it's more stable, and then the hydrogen, which is more electronegative than boron, gets attracted with its electrons to the more substituted carbon. Okay, so to complete our mechanism here, we form a new bond between carbon B and boron, and then we form a second bond between hydrogen and carbon. And in terms of mechanism, it basically looks like hydrogen is taking its electrons, leaving, and then attacking carbon A. But realize that this H minus is a terrible leaving group. It's not just like lifting off by itself. It's being directly handed off from boron to carbon in that transition state. So H minus never really forms. What you have is just this transition state where all of this stuff is going on at once. Okay, so let's draw the product of that first step, hydroboration, oxidation. I'm sorry, the product of hydroboration is as follows. You add hydride to the more substituted carbon, and you add BH2 to the less substituted carbon. So regioselectivity, because the carbon-hydrogen bond ends up on more substituted carbon, they call this anti-Markovnikov. But that name is deceptive because the reason why it's that way is the same as the reason why the other reactions go the other way. Look at the difference between hydroboration, oxidation, this first hydroboration step versus the first step of adding HCl. Notice that when we add HCl, the pi electrons attack hydrogen. That's an electrophilic hydrogen. That's like H+. Whereas in hydroboration, the pi electrons attack boron, and then H- gets delivered. So this reaction's regioselectivity is still driven by the buildup of positive charge. The only difference with this reaction is you're using a reagent that delivers H- instead of H+. Stereoselectivity, you get exclusively the syn product, and that is because this four-membered ring transition state is too small for boron to attach to one side and hydrogen to attach to the other. And so they have to be delivered from the same side. And then in terms of enantiomers, you're going to get a 1-to-1 mixture. So I guess I'll just draw the other enantiomer. Syn addition of hydrogen and boron across the pi bond with hydrogen ending up on the more substituted carbon. All right. Now, who cares about boron compounds? They're useful for lots of reasons, but the one that matters most for what we're going to talk about is the oxidation reaction. And the mechanism for this reaction is known, but I'm not going to require you to know it. I think I maybe put it in the study guide just as because if there are any of you out there who are like a young Josh Price, I always felt if I didn't see the mechanism, I didn't really understand the reaction. So I put it in there for what it's worth, but you don't have to know it. This second step, which is the oxidation step, involves hydrogen peroxide, sodium hydroxide, and water as the solvent. And what this does is it replaces the boron with an oxygen in a way that retains the stereochemistry. So this is going to look like magic alakazam chemistry because we're simply swapping out the BH2 for an OH group. And I could show you how that happens, but it's not important for this class. So this reaction you probably will need to memorize. All this does is it replaces BH2 with OH and does not change stereochemistry. And so if you compare what I've just shown you for this 1-2 punch of reactions, that is, we start with this methyl cyclohexene, we do first hydroboration and then second oxidation, and we get the OH on the we get the OH on the less substituted carbon, and then compare that to what we did before with adding of, sorry, I guess I'll just draw it here. If we take the same starting material and attempt to do the reaction under acid catalyzed conditions, catalytic. When we say catalytic, we mean we don't actually have to add 1 mole of sulfuric acid for every mole of alkene. In fact, we only add a very little bit. But remember, the selectivity here is that the OH ends up on the less, dang it. The selectivity here is that the OH ends up on the more substituted carbon, the hydrogen ends up on the less substituted carbon. The reason for that is that we go through a carbocationic intermediate that looks like this. Okay, so these two approaches and the other difference is that there's no selectivity for syn versus anti for addition of water across the double bond. So these two methods are complementary. If you want the OH on the more substituted carbon, you choose this method, acid catalyzed hydration. If you wanted the OH on the less substituted carbon, you choose hydroboration oxidation. Yeah?
Just to make sure I'm following, the H that jumps on first is from the H2SO4, and then it picks up an H from water.
So it picks up OH from water. So yeah, what likely happens, and when the acid is catalytic, it could be H3O plus or it could be H2SO4. Doesn't really matter. I will often just abbreviate it like that. And then that leads to here, and then water can come in from above or below. That will give us the protonated version of our product. And then we will regenerate our acid catalyst. And as I said, it doesn't matter what does the deprotonating. It's most likely water. And that will give us the product. Okay? Other questions? Yeah?
We're looking for the reagents that indicate the oxidation. There needs to be the hydrogen peroxide, the sodium hydroxide, and water.
Yep. Yep, you need... and frankly, water you can sort of probably leave off there. It's sort of implied anytime you have sodium hydroxide because that's what NaOH is soluble in. But you do need both, the peroxide and the base. Okay, yes?
And carbocation rearrangement in rings only happen if one is they're both axial or equatorial.
Can carbocation rearrangement happen in rings? So this is an interesting question. Are you thinking about maybe this issue where you have a positive charge here and maybe you have a methyl group there that doesn't line up as well as the hydrogen?
Yeah. I'm just wondering if there's
That's a good question. I actually don't know the answer in the sense that because this six-member ring has a positive charge, it's no longer a pure cyclohexane. That carbon is sp2 hybridized. That's going to change the conformational equilibria of the ring, so it may mean there's less of a difference between axial and equatorial. You can envision situations where that might be an issue. I can't think of any that I would, in my nefariousness, give you to worry about on an exam. Yeah. What else? Okay. So practice those 5 reactions. Practice the regiochemical and stereochemical issues associated with these reactions.
Question real quick.
Yeah.
We were doing problems in the book. It looked like aromatic rings could not be halogenated or anything like that.
Yeah. So one of the interesting things about this chapter is not all double bonds are equal. Whereas if you take just cyclohexene, as I said before, and do bromination as an example, you get the anti-vicinal dibromide with its enantiomer. If you use benzene, the benzene sits there and stares at you. And the bromine doesn't get consumed. The reason for that is benzene has 3 double bonds in a fully conjugated ring, and you will learn in 352 that there is a special bonus stability you get when you have a fully cyclic conjugated ring, provided that it has the right number of electrons. Has to do with completely filling all the bonding orbitals and none of the anti-bonding orbitals, and not having unpaired electrons. But that'll come in a later chapter in 352. Just realize for this time, if you see the benzene ring, it's not going to react with alkene addition conditions. You can get this to do something, but you need a reagent to sort of soup up how electrophilic the bromine is, and what happens is actually not an addition reaction. It's a substitution reaction, which we won't talk about. Okay? All right. There's a few little synthesis issues that come in Chapter 10 that I want you to be aware of. They're somewhat tangentially related to what we've talked about so far. The product that I just drew for you, the product of halogenating an alkene, is known as a vicinal dibromide because you have bromines on vicinal carbons. Of course, if we did halogenation with Cl2, you would also end up with the vicinal dichloride. So vicinal dihalide is the product. Sometimes it's useful to recognize structural patterns in products and associate them with specific reactions. So I don't know whether this will help you or not. If it doesn't, don't worry about it. But it can be useful to know that bromination of alkenes gives you the vicinal dibromide with anti-stereochemistry. And then if you see anti-stereochemistry in a product, then you might think, oh, if I wanted to synthesize that, I could use the bromination reaction. In any case, what are vicinal dibromides good for? I don't know is the first one. Not much, perhaps, but other than a demonstration of stereochemical issues. But there is one that's useful in synthesis. So I'm just going to show you a simple addition of bromine to an alkene. and the alkene is just ethylene, 2 carbons. There are hydrogens there that are implied but not shown. And if I do bromination of that alkene, I get this vicinal dihalide. Now, if I use a really strong base, and if I use enough of it, I can do some unique and interesting chemistry. So notice that this dihalide, if we'll color this bromine pink and this bromine blue, and then we'll use pink to say this is the alpha carbon to the pink bromo group, this is the beta carbon to the pink bromo group. Then we will do the same thing with the blue color. This is the alpha carbon to the blue bromo group and the beta carbon to the blue bromo group. Do you see how both of these have beta carbons? Sorry. Duh. Do you see how both of these have protons beta to the bromide? So this is a situation where you could potentially do an E2 reaction, right? You have a proton anti to the leaving group, you can do elimination chemistry. Now, I haven't drawn them anti to each other at this stage, but you should be able to rotate freely around this carbon-carbon bond in order to get each of these beta protons anti to the leaving groups. So suppose I did one elimination reaction. I'm going to redraw the molecule in a way that maybe will make a bit more sense. Suppose I have a really strong base and I do an E2 reaction. And that gives me the following molecule. But I still have a situation now where I have a proton that's beta to a leaving group. Now, back in chapter 7 and 8, we did not do E2 reactions on what are called vinyl halides. Vinyl carbon is the carbon that's involved in the double bond. We did not do E2 reactions on vinyl halides, mostly because I think it didn't fit in there particularly well. But if your base is strong enough, you can have the base remove a second proton to kick off the second bromo group, and that generates, via another E2 reaction, that generates the triple bond. Okay? So this reaction sequence where you have two E2 reactions in series, I'm calling these tandem E2 reactions of the vicinal dihalide to give you first the vinyl halide and then the alkyne. Except that's not an H, is it? Alkyne. Weird. Alkyne, right? And so what kind of base do we want to use? Your text proposes a couple of options. I think I will give you one, and this is NH2 minus Na plus. This is an ionic compound. It will often be written NaNH2. It's called sodium amide. And remember, the negatively charged NH2 amide is a very strong base. And the reason for this is its conjugate acid, ammonia, has a pKa of around 38. So this is on the really, really stronger side of bases. And you need a strong base not only to do these two E2 reactions. So ideally you would need, for every mole of starting material, you would need 2 moles of sodium amide in order to do the tandem E2 reactions. But the problem with using only 2 equivalents is that there's another thing that sodium amide can do to this product. So, and what I'm going to show you now maybe is going to start to look familiar because it goes all the way back to chapter 2. An acid-base reaction can happen wherein amide anion removes a proton from the alkyne to give you the acetylide anion. And how this happens is just we remove the proton and the electrons go on the carbon. Recall that the pKa of the alkyne proton is 25, whereas the pKa of the ammonia proton is 38, which tells you that this reaction is really favorable. So unless the reaction is instantaneous, if it's slow at all, as soon as I start forming some of this alkyne, it's going to go and get deprotonated like that. And that sets up a situation where if I only use 2 equivalents of base, I'm going to end up with a mixture of deprotonated alkyne and vinyl halide and dihalide starting material because I've consumed some of my reagent on things I wasn't anticipating. So what we typically do in this case is we're going to use 3 equivalents. That means 3 moles of sodium amide for every mole of vinyl dihalide. And the third equivalent is going to remove the proton from the alkyne. And we do this simply to drive the reaction to completion without worrying about mixtures of byproducts. And this is convenient because most of the time what we want with the alkyne is just to remove the proton anyway. So to make it a good nucleophile, right? So typically we'll use 3 equivalents of sodium amide to convert the dihalide into an alkyne nucleophile. Right? Yes?
So just to clarify, at the end of the whole reaction to 3 equivalents, both of the carbons will have negative charge.
At the end of the reaction, both of the carbons will have a negative charge? No. The 3 equivalents are here. 1, to remove 1 beta proton and leaving group leaves. 2, to remove the other beta proton and leaving group leaves. And then the third and final, to remove 1 of the protons of the alkyne. Once the alkyne is negatively charged, the pKa of the second proton goes up dramatically. And you learned about this in general chemistry. The first proton on sulfuric acid is easier to come off than the second one, and so on. Yeah?
So why does it have to be like a really, really strong base to get to?
Why does it have to be a really, really strong base? I don't know, though my intuition says maybe this E2 reaction is slow. I don't know why. I don't have a rationalization for it. So, and sometimes in chemistry we don't. The bottom line may be that this reaction works. The other possibility is that there are other reagents that do it better, and they're keeping it simple in the text. So, yeah. Okay, so now we know how to make an alkyne. We should just review briefly the kinds of things you can do with acetylide anions. And so what can you do with an acetylide anion? What we're going to do right now is mostly substitution chemistry. So if we have some kind of alkyl halide, and we would usually want it to be a primary alkyl halide to avoid the potential for an E2 reaction, because this is a good, strong nucleophile, but it's also a good base. So we want to avoid the potential for elimination. So if we stick to primary alkyl halides, SN2 is fast. And this SN2 reaction gives us a new carbon-carbon bond. And that may not mean a whole lot to you, but for organic chemists, anytime we do a reaction that makes a new carbon-carbon sigma bond, we all sort of go, ooh. Because if you want to generate complicated molecules, like some of the weird molecules that we isolate from nature, strange natural products, you have to be able to make a lot of carbon-carbon bonds. That's how you build up structural complexity. So this is one of the ways we can do that. It's maybe the first way that we've learned this semester, perhaps aside from using CN- as a nucleophile. R can be a lot of different things, but it's best if the carbon attached to the bromo group is primary. Okay. Interestingly, the alkyne, at least acetylene, the C2H2 comes with 2 protons. And so if I want to, I can take this alkyne that I just made and I can use a base that's strong enough to remove the proton from an alkyne. And then I can do another substitution reaction to put another group on that other carbon. Some people don't fall for the trap of thinking there's a difference between these two. That's not cis or trans. These are sigma bonds. You can rotate freely around those sigma bonds. Remember that alkynes are sp hybridized. You have linear geometry about this carbon. So this carbon, that one, and that one are all in a straight line. Sometimes if you want to do skeletal structures with alkynes, it gets a little confusing. And I've seen inexperienced students make this mistake where they think they get confused about how many carbons we're talking about there. You can even actually connect the line completely, and you just need to realize that these two are the same thing. Okay? Yes?
This is maybe unrelated, but is this style of reaction similar to like making plastics?
Is this style of reaction similar to making plastics? In a way, yes. The idea of being able to do the same reaction a couple of times to build up complexity. Though we're going to see when we talk about radicals, which we were going to do this semester. Oh, that's another thing we got to get in. Dang. We won't do a ton on it. Don't worry. But this isn't, a lot of plastic formation involves like chain reactions, like things that can happen in a repetitive fashion. And this one, essentially, once you do 2 carbon-carbon bonds, you're done. All right, what else? Okay, so I want you to be thinking about the kinds of things you can make with not only making the alkyne, but then using the alkyne to make other molecules. For example, if I had some alkyne like this that I had already deprotonated, I can open up epoxides with alkynes. So as an example, and this would be a strong nucleophile, so if there were any regioselectivity issues here, you'd expect the alkyne to add to the less substituted carbon because of sterics. And then you would have aqueous workup, usually to add a proton to the alkoxide that you formed. Oops, we're running out of space. And we've got that familiar pattern that we see when we open up epoxides, this 1-2 relationship between OH group and then whatever your nucleophile was. All right. So sometimes on synthesis problems, somebody might say, okay, I want you to make this alkyne using only all of the carbons in the alkyne have to come from this alkyl halide. Only source of carbon. It's fine to use any other reagents, but each of the 6 carbons in this product must come from this source. So if my source only has 2 carbons, but my product has 6, I know I'm going to need to make some carbon-carbon bonds to stitch a couple of those together, right? So how would I do that? You can approach synthesis problems in a couple different directions, and really it's about thinking forwards and backwards until you can meet in the middle and complete the chain. What I'm talking about here is I might say, I would look at this product and I might ask, are there any bonds in this product, carbon-carbon bonds, that I know how to make? And I know I have to make carbon-carbon bonds because my starting material only contains 2 carbons. So what bonds do I know how to make? And I would need to remember that I know how to make a bond between an alkyne carbon and an adjacent sp3 hybridized carbon. That's just an SN2 reaction. So I'm using here an arrow that's different from our reaction arrow. This is sometimes called a retrosynthetic arrow. This is a conceptual step backwards to what the starting materials would have been if this is the product. And so I'm going to draw the alkyne, the deprotonated alkyne, and the alkyl halide that I might use to do this reaction. And I'm going to demonstrate that it is an SN2 reaction. And I'm going to note that already I have used, at least on this side, I'm already back to an allowed starting material. Okay, so to see sort of conceptually what we did there, thinking backwards in a synthesis I think is a challenging skill to master. So questions, what questions do you have? Yes?
If the only source of carbon is the alkyl halide, then the 2 carbons that have the triple bonds, those don't come from the alkyl halide, do they? Or are we going to get there?
The question would be, could you make the triple bond starting with the alkyl halide? Yep. So we're going to get there. Other questions? The dumb thing about synthesis is when we're working through it together, it seems self-evident, and you're like, oh yeah, okay, that makes sense. But when you're on your own, and it's easy to forget. And so being able to do synthesis problems involves some more detailed familiarity with the reactions than you may have developed yet. So far in the class, I've told you focus on the why, focus on why reactions happen. That will help you understand how they happen, which is mechanism, and then that helps you predict what happens. So that if you forgot about hydrohalogenation as an example, if you start with HOMO attacks LUMO, you can pretty well figure out what's going to go on in that reaction. However, when you're planning a synthesis, you need to be familiar enough with the reactions that sort of starting materials, products, and reagents are just at the top of your mind. So that's why I told you earlier it's useful if for each reaction we talk about, you can think in terms of starting material and reagent, what is the product? Starting material and product, what was the reagent? And perhaps more usefully, product and reagent, what was the starting material? You put all those together and then you're prepared to answer this question, which is product, no reagent, no starting material. What's a reasonable step backwards? Right? So, and with each step backwards, I would remind myself that, oh, I can get that deprotonated alkyne from a simple acid-base reaction. Okay, and each step backwards gives me a new problem. I now have to ask, okay, I got 4 carbons. Are there any bonds there that I know how to make? And by comparison with what we did above, hopefully it's clear that you can go backwards to this deprotonated alkyne and this alkyl halide, again via an SN2 reaction. So we've used 2 of this starting material. All right, so where am I going to get the deprotonated alkyne from? Simple acid-base chemistry, good. Okay, now we just learned this. Where do I get this alkyne from? Do you remember what the starting material was and what the reaction was? Okay, so we did this. We had the vicinal dihalide, and then we did the 2 E2 reactions to get the alkyne. And then we also deprotonated the alkyne to get this nucleophile, which we just barely used. So that means I can take the alkyne and I can go back to the vicinal dibromide, and this is going to be the tandem E2 reactions, probably using NaNH2 as base, and probably instead of going here and then here, we're just going to go all the way there in one step. Okay, we're closer to our starting material, but we're still not there. Oh, and any questions about this step? You just as well, go ahead. You just as well work on that until you've got it, because that's, I can guarantee this showing up on a future exam. Yeah.
Is it more appropriate to just sum up all the steps like this, or do you want us to go through all the steps like we did in the previous example, like writing all the steps?
Okay, good question. So in a synthesis problem, if you were writing it out on paper, what we're doing here is we're sketching out the pathway, and then we would write it in the forward direction. But we wouldn't need to draw the mechanism of each step, unless you wanted to, but that's not required. Now, on a multiple choice exam, the way I tend to do synthesis problems, it's more of which of these syntheses will work versus which are wrong, or fill in the missing reagent, or fill in the missing intermediate. So it won't be like staring at a single molecule and a blank piece of paper, but the skill to be able to deal with the situation where you got a blank piece of paper and a complicated molecule, and can you synthesize it, will help you be successful on the exam. So where do we get this? Go ahead.
So sorry, so it's just enough to say that the NH2 is just the reagent to turn the bromine one into the triple bond.
Yes.
Those 2 reactions.
This is just, I'm just reminding myself that I know that if I start out with 3 equivalents of sodium amide, I'm going to make the alkyne through 2 successive E2 reactions and then a final deprotonation to give me this. Yeah. It may have been better ultimately to just do this. Say, and if I use 3 equivalents of NaNH2, I'm going to do first the 2 E2 reactions, and then I'm going to do the deprotonation. All right, where do I get the vicinal dihalide from? The bromines on adjacent carbons. Yeah?
So going back, we're using three equivalent bases for 2 E2 reactions?
For the two E2 reactions and the deprotonation, that will get you all the way to this acetylide anion. That's basically what we did up here.
Is it the, oh, I'm moving on to the next one.
Okay. Other questions? Okay, what's my starting material for the vicinal dihalide?
2 double bond carbons and BR2.
The alkene, yep, and Br2. Okay. Still not the starting material, but can I get this product from this starting material? What is that? Yeah, E2 reaction. Probably I want to use tert butoxide, which is a sterically hindered base, so that I don't have to deal with competing elimination reactions. But there you go. We've completed the chain, and all of our carbons have come from instances of this starting material. Okay, so what now might be good for you to do in your own studies is to write this synthesis out now in the forward direction. We've sketched this out. This is called a retrosynthetic analysis, and it's something that is near and dear to the heart of the author of your text because her PhD advisor was one of the people who sort of invented it. But it's a way of breaking down a large problem into smaller and smaller problems. Okay, I think that concludes what we're going to do in chapter 10. So let's take a break.
That's the end of exam 3.
That is the end of exam 3.